Hello guys, welcome back to my channel. This is your host, and today we're going to discuss about India's next space mission, Aditya L1. After the successful launch of Chandrayaan-3, India has launched its new mission Aditya L1 on 2 in September. So let's get started. The word Aditya is Sanskrit word which means sun. Before understanding the project, we have to understand about the sun. The sun lies at the heart of the solar system, where it is by far the largest object. It holds 99.8% of the solar system's mass and is roughly 109 times the diameter of the Earth. About 1 million Earths could fit inside the sun. The surface of the sun is about 5,500 degrees Celsius hot, while temperatures in the core reach more than 15 million degrees Celsius, driven by nuclear reactions. One would need to explode 100 billion tons of dynamite every second to match the energy produced by the sun, according to NASA. The sun was born about 4.6 billion years ago. Many scientists think the sun and the rest of the solar system formed from a giant rotating cloud of gas and dust known as the solar nebula. As the nebula collapsed, because of its gravity, it spun faster, flattened into a disk. Most of the material was pulled toward the center to form the sun. The sun and the atmosphere of the sun are divided into several zones and layers. The solar interior, from the inside out, is made up of the core, radiative zone, and the convective zone. The solar atmosphere above that consists of the photosphere, chromosphere, a transition region, and the corona. Beyond that is the solar wind, an outflow of gas from the corona. The core extends from the sun's center to about a quarter of the way to its surface. Although it only makes up roughly 2% of the sun's volume, it is almost 15 times the density of lead and holds nearly half of the sun's mass. Next is the radiative zone, which extends from the core to 70% of the way to the sun's surface, making up 32% of the sun's volume and 48% of its mass. Light from the core gets scattered in this zone, so that a single photon often may take 1 million years to pass through. The convection zone reaches up to the sun's surface and makes up 66% of the sun's volume, but only a little more than 2% of its mass. Roiling convection cells of gas dominate this zone. Two main kinds of solar convection cells exist: granulation cells, about 1,000 kilometers wide, and supergranulation cells, about 30,000 km in diameter. The photosphere is the lowest layer of the sun's atmosphere and emits the light we see. It is about 300 miles, 500 km, thick, although most of the light comes from its lowest third. Temperatures in the photosphere range from 6,125 degrees Celsius at the bottom to 4,125 degrees Celsius at the top. Next up is the chromosphere, which is hotter, up to 19,725 degrees Celsius, and is apparently made up entirely of spiky structures known as spicules, typically some 1,000 km across and up to 10,000 km high. The sun's magnetic field is typically only about twice as strong as Earth's magnetic field. However, it becomes highly concentrated in small areas, reaching up to 3,000 times stronger than usual. These kinks and twists in the magnetic field develop because the sun spins more rapidly at the equator than at higher latitudes, and because the inner parts of the sun rotate more quickly than the surface. These distortions create features ranging from sunspots to spectacular eruptions known as flares and coronal mass ejections. Flares are the most violent eruptions in the solar system, while coronal mass ejections are less violent but involve extraordinary amounts of matter. A single ejection can spout roughly 20 billion tons of matter into space. In 1990, NASA and the European Space Agency launched the Ulysses probe to make the first observations of its polar regions. In 2004, NASA's Genesis spacecraft returned samples of the solar wind to Earth for study. In 2007, NASA's double spacecraft Solar Terrestrial Relations Observatory (ESTEREO) mission returned the first three-dimensional images of the sun. NASA lost contact with STEREOB in 2014, which remained out of contact except for a brief period in 2016. STEREO remains fully functional. The Solar and Heliospheric Observatory, SOHO, which last year celebrated 25 years in space, has been one of the most important solar missions to date. Designed to study the solar wind, as well as the sun's outer layers and interior structure, it has imaged the structure of sunspots below the surface, measured the acceleration of the solar wind, discovered coronal waves and solar tornadoes, found more than 1,000 comets, and revolutionized our ability to forecast space weather. The Solar Dynamics Observatory, SDO, launched in 2010, has returned never-before-seen details of material streaming outward and away from sunspots, as well as extreme close-ups of activity on the sun's surface and the first high-resolution measurements of solar flares in a broad range of extreme ultraviolet wavelengths. The newest addition to the Sun observing fleet are NASA's Parker Solar Probe, launched in 2018, and ESA/NASA Solar Orbiter, launched in 2020. Both of these spacecraft orbit the Sun closer than any spacecraft before, taking complementary measurements of the environment in the vicinity of the star. During its close passes, the Parker Solar Probe dives into the Sun's outer atmosphere, the corona, having to withstand temperatures hotter than 1 million degrees Fahrenheit. At its nearest, the Parker Solar Probe will fly merely 4 million miles, 6.5 million km, to the Sun's surface. The distance between the Sun and Earth is 93 million miles, 150 million km. The measurements it makes are helping scientists learn more about how energy flows through the Sun, the structure of the solar wind, and how energetic particles are accelerated and transported. While Solar Orbiter doesn't fly as close as the Parker Solar Probe, it is equipped with high-tech cameras and telescopes that take images of the Sun's surface from the closest distance ever. It was not technically possible for the Parker Solar Probe to carry a camera that would look directly at the Sun's surface. At its closest, Solar Orbiter will pass at about 43 million km away from the star, about 25% closer than Mercury. During its first perihelion, the point in its elliptical orbit closest to the Sun, the spacecraft approached the Sun to about half the distance from Earth. The images acquired during the first perihelion, released in June last year, were the closest images of the Sun ever taken and revealed previously unseen features on the star's surface, miniature flares dubbed the campfires. After Solar Orbiter completes a few close passes, mission controllers will start elevating its orbit out of the ecliptic plane in which planets orbit to enable the spacecraft's cameras to take the first ever close-up images of the Sun's poles. Mapping the activity in the polar regions will help scientists better understand the Sun's magnetic field, which drives the 11-year solar cycle. Lagrangian points, often referred to as L points, are specific positions in space where the gravitational forces of two large objects, such as the Earth and the Moon, or the Earth and the Sun, balance the centripetal force felt by a smaller object, like a satellite or spacecraft. These points were named after the Italian-French mathematician Joseph Louis Lagrange, who first studied them in the 18th century. There are 5 Lagrange points labeled L1 through L5, and each has unique properties. 1. Lone. The first Lagrange point is located between the two larger masses. At this point, the gravitational forces of the two masses cancel out, allowing a smaller object to remain in a relatively stable position. L1 is often used for solar observatories, such as the SOHO, Solar and Heliospheric Observatory. 2. The second Lagrange point is also located on the line connecting the two larger masses, but on the opposite side of the smaller mass. L2 is used for telescopes and observatories like the James Webb Space Telescope, JWST, because it allows for continuous viewing of distant objects without the interference of Earth's atmosphere. 3. L3. The third Lagrange point is located on the opposite side of the two larger masses from L2. However, L3 is unstable, and objects placed there tend to drift away over time. There are no known missions or objects currently at L3. 4. L4 and L5. These are known as the Trojan points and are located 60 degrees ahead of and behind the smaller mass in its orbit around the larger mass. These points form an equilateral triangle with the two massive bodies. L4 and L5 are stable and have been used by some natural satellites, such as the Trojan asteroids of Jupiter and some recently discovered Earth-Trojan asteroids. Lagrangian points are critical in space exploration and satellite positioning because they allow spacecraft to maintain a relatively fixed position relative to the Earth and other celestial bodies with minimal energy expenditure. These points are valuable for scientific research, space observatories, and even future space habitats and space missions beyond our planet. Aditya L1 is the first space-based observatory-class Indian solar mission to study the Sun. The spacecraft is planned to be placed in a halo orbit around the Lagrangian point 1, lone of the Sun-Earth system, which is about 1.5 million km from the Earth. A satellite placed in the halo orbit around the L1 point has the major advantage of continuously viewing the Sun without any occultation. This will provide a greater advantage of observing the solar activities continuously. Medium. The Aditya L1 mission carries a suite of 7 scientific payloads to carry out systematic study of the Sun. The Visible Emission Line Coronagraph, VELC, studies the solar corona and dynamics of coronal mass ejections. The Solar Ultraviolet Imaging Telescope, SUI-T payload images the solar photosphere and chromosphere in near ultraviolet, UV, and also measures the solar irradiance variations in near UV. The Aditya Solar Wind Particle Experiment, AACPEX and Plasma Analyzer Package for Aditya, a PAP payload study the solar wind and energetic ions, as well as their energy distribution. The Solar Low Energy X-ray Spectrometer, SOLEX, and the High Energy L1 Orbiting X-ray Spectrometer, HEL10S, studies the X-ray flares from the Sun over a wide X-ray energy range. The magnetometer payload is capable of measuring interplanetary magnetic fields at the L1 point. Hope this mission unveils the hidden knowledge of Sun. And that is it. Thanks for watching. If you like this video, please like, share, and subscribe, and hit the bell icon for more interesting videos.